All right. So I wanted to use today to please answer show. So someone asked, like, I think it'd be helpful if we went through things together. So you just did comprehension check two. Pick anything and I'll do it on the board like with you together. So what is something that you're like, I don't fully understand? When you looked down the comprehension check and you were like, oh, I got that one wrong, or anything. I'm trying out this new technology. I don't know if the recording's going to work like this, but we're going to take my wife's iPad and we're going to see if this works. Is that a hand?
Yeah.
All right. Which one? What do you think?
Questions.
Pick something.
5, 6, and 7 hard, so any one of those.
On the problem set? Okay. Let's pull out one of those. That's problem sets. Assignment. Problem set 3. Stuff. All right. Let's start with, I'm going to start with 5. Okay. So number 5 says a researcher wants to know if a specific third grade child who participated in a new study skills program performed differently on an achievement test than students who did not participate. The researchers notice that the score for third grade children on the test is normally distributed with an average score of mu 150 and a standard deviation of sigma 12. The researcher collects a sample of 4 children who participate in the program, and they earned an average of M 181. Okay. It's handy. But why don't we write down the things we know about this problem? So what we know is, geez, no, right on this thing without like touching it. So U, it's going to be our mu, is 150. Ooh, all right. Kind of hard to read. Let me zoom in a little. Okay. And our sigma, so like the standard deviation of the population, is 12. I see the word differently. And so that's telling me something. What is that telling me? So the problem uses the word differently. Two-tailed test. Two-tailed. I know that my sample population has a mean of 181. And there seems to be some information provided to me about this n equals 4. I studied 4 people, or have 4 sample of 4 children. I also know that the alpha being provided is 0.01. And we know it's two-tailed. So when we're thinking about that, here's our curve. An alpha of 0.01 for a two-tailed test, how much area is on one side of that curve? Point 0.005, right? We divide it by 2. So first thing I do, I read the problem. I'm going to write down as much information that I know about it. So I know that side is 0.005. So likewise, this side is going to be 0.005. And here's our line down the middle. Okay. Push it this way a little bit. Great. For me, I feel like the first thing I think about when I see this problem is what information was I given versus what information am I lacking? That's going to help me figure out what I need to do. And there's a really important value that seems to be missing from this example that I would otherwise like to have. Besides things that like I could solve for. I know the samples mean, but I don't know the samples. Standard deviation, right? I don't have any information about the sample standard deviation. So already now when I'm looking at my formulas, the formula sheet gave us like two possible options for formulas when it comes towards like a mean and the population mean. So what I do know is I know I have a, oh my God, no, I can do this. Stay near the iPad. I have a population mean here. And I have my sample mean here. And I have two really important pieces of information already. And so I look at my formula sheet in front of me, and the formula sheet has two formulas that seem like they could be helpful to me. One says Z equals X minus mu divided by sigma. And the other one says Z equals X minus mu divided by sigma m. And I'm told on the formula sheet that sigma m represents this divided by n. Where yeah. What formula like uses all of the information that we have? Yeah. The second one. Why the second one? Great. So we can use the formula to find it, right? What we have here is sigma sorry, um, sigma and our n. We have our x and our mu. One thing I noticed as I was going through the comprehension checks is we might be forgetting and mixing up what x means sometimes. And I understand why. Because it's not using a letter that you might want it to be using. In this problem, what is x? Because if we look at all the information I've written down, I have not written down x. I can see why that would be confusing. But what does x? Where's x here? In all the information, when we look at these formula sheets, we're like, Dr. C didn't give me an x, I don't know what to do. What is x?
Sample population.
The samples mean, yeah, the sample population mean. I shouldn't have wrote population there, sample mean. That's on me. Let me find that here. Thank you. But the sample mean, right? The sample mean is our X. And it's our X because that's what we're comparing. That's what we have. That's our observation. We have one sample. The sample has an average. And we're going to subtract it. We're going to compare it against this other thing. Okay. So now that we know maybe what we're looking at, where am I? No. Let's plug in what we have. So I have, where's my pen? Where's my pen? No, there it is. Okay. Z equals C equals X, which is 181. Why don't I just have the problem set open on my laptop? Minus 150 divided by the standard deviation is 12 over the square root of n, which we know is 4. So then that's going to be 12 over 2. Wait, what am I doing? Yeah, sorry. Just wanted to make sure I was doing this correctly. It's 6. And then 181 minus 50 is 31. Or 5.16 repeating. 1.6 repeat. All right. So now we've gotten something. This comes to the next piece of where I think there might be some confusion. So here's all of our information. I'm going to take some bit of information and write it down because once I solve for something, I like to write down what I've learned. I know my z-score is 5.16. What does that mean? What is, oh, sorry, let me scroll over. Now written down 5.16. We solved, we got a z-score of 5.16. What is a z-score of 5.16? What does that mean? Truly the definition of a z-score. Yeah.
Your 5.16 standard deviation.
You're 5.16 standard deviations away from the mean. Okay. You can actually get one little extra piece more accurate. That is like 99% of it, but not just away from the mean. Right, positive, higher than the mean, right? We know that because it's positive. It's not a negative sign there. Right. So when we do this formula, the first thing that we're doing is we're trying to understand what is our z-score. And 5.16 standard deviations away from the mean is what we are looking at, the score of 181. Right? That is 5.16 standard deviations away from the average. That is not our cutoff score. And this is where there's some confusion coming up as well. You have to basically find like two different z values. The first one is our z-score. Where does our average fall? And the second is where are we allowing ourselves to be, right? So if we're here at 5.16, that's some value. A second question is, what piece of this represents, like what z-score is it to have 0.005 to the right side? Right. That is a question we don't yet know the answer to. So how can we find that out? How do we find what our z cutoff is? We have an alpha of 0.01, and we said it's a two-tailed test. So we need to know something about 0.005. Where am I looking? Yeah. The z table. Thank you, Kylie. Yes, the z table. And so when we go to the z table, here is another piece where I think we're making some errors where I'm gonna pull up, let me just download this here. Now, the recording doesn't get to see the z table. That's okay. We said the alpha was 0.01. We then said it's a two-tailed test. So the alpha is 0.005. And what is alpha range between numbers? Can we have a negative alpha? Have we ever seen a negative alpha yet? How about that? I don't think so. So like positive what though? What was like the highest that it could be? Yeah. 1, right? So we know our alpha ranges between 0 and 1. That's what, and what does that represent? That's our area under the curve, right? Alpha is a proportion. It is the proportion under the curve. And so when we say in alpha of 0.01, we're saying 1% under the curve. And then we said it's a two-tailed test. So it's 0.5%, or 0.005 over there, and 0.5% or 0.005 over here. On your z tables, does it tell you percents or proportions? What does this say? Percent. This was tripping people up a little bit too, I noticed. So when we're looking for percent, and we know we're looking for in the tail, you have to look at this alpha 0.005 in your head, just like write it down. What does that mean? It means 0.5%. I need to find the number 0.5 in this table on this column. Because what I'm asking is, what is the z-score such that the percent in a tail, is 0.5%. And so I'm going to scroll on this page, it looks like somewhere. So what is the z-score such that 0.5% lies in the tail?
Plus or minus 2.58.
Right here, plus or minus 2.58. Because we can look across, and here is 0.49. That's the best we can do with our table to get us close to, even a little bit under 0.5%. Now we have a second number. So let me go back to my iPad and write that down. Here. Ooh, wake up. So our second number that we've learned is the Z, and I can even write down to myself, cutoff is plus or minus 2.58. Oof. Oh man, that's bad. Sorry. First time using it. Yeah.
This might be like a solution, but most of like the workouts, the alphas and points are one, so would this never be the same for like the cutoffs was the same for like most of these workouts?
That's not a silly question. It's a great question. Let me just finish trying to rewrite cut off. I'm just going to write CO 2.58, and it was plus or minus. So, wonderful question. Is this like something I can kind of like memorize in a way, right? And totally reasonable. Yes and no. So, you are right that we tend to use 3 different alpha values. In class, like I've only ever asked you 3 different things. I've asked you alpha of 0.01 and alpha of 0.05. And I don't think we've ever had a problem with it, but we might of 0.1. And indeed, you could memorize that if this is two-tailed, then the cutoff score is plus or minus 2.58. It is a different number if it's one-tailed. And likewise, you could memorize that this is plus or minus 1.96. However, what we're learning this week is these numbers are correct for z-scores, which, oh, now I'm forgetting the number that we're using, is, I think, which is a t-score if your n is greater than 120. In our t-distributions, doing t-tests, if we hear the word t-test, our cutoffs are not always as consistent. It depends on how many people we've sampled, and it only looks like a z-score if you've sampled 120 people. If not, then you can't rely on these like things. So yes, for the z stuff, these are easy to memorize, not exactly for the t. But they're useful. They are. Okay. So we know our z cutoff was plus or minus 2.58. And then we said our score that we received was 5.16. Before we move forward, we already can do, like in our heads, a quick understanding. Do we think that we are able to reject the null hypothesis at this point? Like, is there a significant difference between what we have observed and the population if we had assumed that the null was true, that there is no difference? And then we pull out this population. Can we say we have evidence to suggest that they might actually be different based on this alone? Shane nods yes. Sarah, why yes?
Because 5 is greater than 2.
5 is greater than 2, right? So we know that our z-score, I'm going to use the board a little bit. Our z-score is a 5, and our cutoff is a 2.5. And if we're just thinking about what does that mean, it means our cutoff score is here at 2.5, 2.58. And so out here, we've just said represents 0.5%. There's 0.5% greater than this number. And our score is all the way over here at 5.16. So what can you tell me about this area, the area to the right of 5.16? What do you know for sure about that area? Is it a larger area than 0.5%? Or is it a smaller area than 0.5%?
Small.
Why smaller?
Is, 2.58.
If this is my whole birthday pie, then what I want to eat is this amount. There's still a little bit left of my birthday pie. This amount. Not as much, because I ate some of it already. So we know it's smaller. And that's just a good eye check for us. When you start reporting like p-values and percentages, you should know that I'm looking for a number smaller, or I'm looking for a number larger. We can use these z-scores to tell us something about what our answer should look like. It's a good like spot check for us. All right, z of 5.16. Do we have that value here on the table? Nope, we do not. Best we have is 4.5. 4.5 is 0, 0. It's not 0. It says 0, 0, it's not actually 0. It's just smaller than a 100th of a proportion. And so 5.16 is going to be smaller or bigger than whatever this number is. Smaller. So it's going to be less than whatever this is. And so we would write, based on the information we have in front of us, it's less than 0.01. I don't know what it is, but I know it's definitely less than this number here, which is 0.01. And that's probably the best I can tell you. Now, at this point, let's go back to the problem. And we have the 5 steps. This came up in the problem set as well. The hypothesis testing one was, please, do this through the 5 steps. You cannot minimize Zoom. I don't want to minimize. So the first part says restate the question as null and alternative hypotheses, both words and equations. Jeez, didn't know I could do that. Okay, be careful. So it says a researcher wants to know if a specific third grade child who participated in the new study skill program to perform differently. The researcher collects a sample of 4 children who participated in the program and they earned an average. So differently, ooh, that was close. We have the true population of kids in the program, and we're going to call this the null hypothesis. If it's a null hypothesis, we're going to compare that against the true average of people, of kids not in the program, no prog. What does it mean to have our alternative or our null hypothesis? They be equal, right? That we're assuming that in the state of the world that they're equal. There is no difference. That's the null. It's boring. Nothing changed. It's a null finding. It's not different. And HA is our alternative hypothesis. And so we have our true average of the program compared to our true average of no program. And we said this is a two-tailed test. So what are we hypothesizing? Yeah. Not equal to, right? They're not equal because we're willing to accept that the program could be better, but it could also be worse. Not equal to. And then you just have to write, so this is in like equation or in, what did I put? Yeah, equation form. This is what it means to write hypotheses in equation form. Having H0, mu program, mu no program, mu program, mu no program, and then just writing that out in words. Second step was to characterize the comparison distribution. Now, why am I doing these steps like at the end? Because if I'm asking you the question, I'm not going to give you a question that you can't then compare, right? But I'm doing it kind of like save time. I want to get to its answer and then walk us back. So characterize the comparison distribution and ask the 3 things: the shape and the measures of central tendency and the variability. What are our 3 measures of central tendency? Yep, shape, the shape, variability, and but like what are the 3 ways which we can define central? What it means to be the middle? Yeah. Mean, median, and mode. And in this class, for the most part, when we're doing stats, we're going to be talking about which of those 3? Mean, right? So when we say central tendency, your mind should just replace the word with mean. Cross it out, write mean. So shape, mean, and variability of the comparison distribution. Compare distribution. We call it this because we're trying to compare against something that we don't fully know all the information about. I don't know my sample standard deviation. Question?
Yeah, for variability, could you use standard error?
That's what we're going to be using.
Okay.
Yeah.
Because that's what I did. I just wasn't sure if
Yep.
that was right.
That is correct.
Okay.
Yes. And variability. So shape, our mean, and our variability. The problem tells us. So actually, let me take a step back. When I see this question or this part, my mind screams out one thing: the central limit theorem, 3 rules. This is literally like the thickest I can make my lines. The 3 rules of the central limit theorem. Our 3 rules of the central limit theorem are that our comparison distribution, its mean is what? I heard someone start remembering correctly.
Equal to the.
Yeah, right. So rule one is that our comparison distribution has a mean that is equal to the population mean. So when I write UM, that represents the comparison distribution's mean, is equal to the mean of the population. And so here, we're basically saying we know that this mean is 150. I did not give you the mean of a comparison distribution, but rule one says you did. It's the population's mean. So 150. Rule number two says that the standard deviation of that population distribution, of our comparison distribution rather, is equal to what? Yes, good. And what was the formula for getting us to 6? Great. All right, so we have our population standard deviation divided by the square root of our sample size. And this thing, standard deviation of our comparison distribution, has another name. That name is called standard error. So these two things are the same. That is why on your formula sheet, I wrote standard error, parentheses, standard deviation of the sampling distribution of sample means. Trying to tell you that like, it represents both names. And so we found out that this was equal to 6. And then rule number 3 says what about distribution shape?
The population is greater than 30. It's normal shape.
Population?
Like that.
N, right? Yeah. So how big of our sample do we have, right? So if sample N is greater than 30, normal. Is our sample N greater than 30? Am I jumping around answering questions right now? We're on number 5. What is our sample N? What? Sorry, I didn't hear that. 4. Is 4 bigger than 30? Okay. Double check around the same page. So our sample is not bigger than 30. What is part 2 of rule 3? What do we do if it's less than 30? Good. This was a big miss on the comprehension checks as well. Right, that if your sample n is less than 30, rule 3 says your comparison distribution will take the shape of the population's distribution. Now, let me kind of jumping around a little bit, but we're taking a good amount of time on this, which I'm happy with, but I just want to make sure we're covering other important things that we, lessons to kind of remind ourselves on. So when we were here and we were looking at our Z cutoff score, we said it was 2.58, right? And that was going to represent this number here. And you told me that that number represents proportion or percent? Percent. Okay. So 0.49 represents 0.49%. I want to know, and where, actually, before I get there, where does this fall again? 0.49% what? Or
So,
in the tail. So if we're looking at a normal distribution like this, 2.59 positive means that over here in the tail, there is 0.49% of the curve. And that means what percent of the curve is at negative 0.258?
negative point.
It's not necessarily negative, but it's just another 0.49%.
Right.
Right? So another 0.49% of the curve is over here. So if looking at this table then, say I want to know, I want to be better than 99.4% of people. That means I want the people below me, people behind me, to be 99.4% of the world on this test. I want to be better than 99.4% of people. Where am I looking? What am I looking for? What is my Z-score that I need to achieve to be better than 99.4% of people? Okay. Erase it because I didn't want you to fall for that trap. You said 2.58? Yeah, nope. You were on the right track, but I switched the question a little bit just to get us thinking about a different number. So 99.4 means how many people am I letting be better than me? 6%, 0.6%, right? Yeah, exactly. I'm okay with having 0.6% of the world be better than me. So what is my z-score that I need to achieve in order to be better than 99.4? I'll try again, yeah.
2.5.
2.51, yes, exactly, right? So here, 2.51, 0.6. Be better than, or to have people be in the top 0.6%. I need to find the area under the curve that is 0.6% larger, higher than that. I don't remember exactly where this question showed up, but I know that we were really confused about this, right? I think it was the z-score from tech, maybe. That's kind of what that one was trying to ask you to do, right? Like think about percentages, use the table, and find the z-scores based on that. Sorry, that one I remembered it when I was creating. I was like, oh, I'm missing this. When we say better, it also helps us think again, like, oh, one tail, right? Like I want only people to eat better than me. And so this is in the tail, right? A single tail. Okay. We did 2, 3, determine the cutoff score. We did that. Calculate our observation score on the comparison distribution. We did that. And to decide whether to reject or fail to reject the null hypothesis and interpret. So we already had, the only thing that we hadn't done, well, we kind of did that as well, is that we knew that, come on. We knew our P was the proportion, oh my God. Where did we calculate that? Up there. Way back here, we calculated our z-score of 0.56, or 5.16, sorry. And we knew that our z-critical was 2.58. This is our z-score. We went to the table and found that it wasn't on the table. And so we knew that the proportion left in the tail, or really, actually, this was the percent left in the tail, based on that table, was less than 0.01%. So we can turn this percentage into a probability by doing what? How do we turn percent into probability?
Yes.
2 points to the left. So 1 and 2 gives us a 0, and a 0. Why am I doing that? 1, 2, 0, 0. I don't think you can do it's less than, yeah, maybe it is. So less than 0, 0, 1, the p-value. Oh, sure. But in psych, we round our p-values to 3 decimal places, not 4. And since we know it's definitely less than 4 decimal places, it's definitely still going to be less than 3. So p is less than 0.001. And we knew our alpha was 0.01. This isn't the best one because it's so big of an effect. But now we can kind of compare. Is our p-value smaller than our alpha? Are they both in proportions? Yes. And so then we can project it. Now, last thing. The definition of a p-value is just like, I literally was scrolling on Reddit last night. And people on Reddit are like being so pedantic on what the definition of a p-value is, and I want to take a screenshot and be like, see, like the nerds really care about this thing. But they're extremely pedantic about what does it mean to have a p-value? What does that thing represent? And lately we've been trying as like statisticians to teach people the exact definition. And one of the comprehension checks asks you to define a p-value. You had to get it in the most annoyingly way possible correct. So what is the definition of a p-value? What do I think P stands for? We just solved for P here. What did that P represent? What kind of P? Probability, all right? So the probability in science, we do what? Observe, right? Probability of observing a value. What value? What do we care about this value? What does it need to be?
Is it if it's more or less extreme than assuming that the null is true?
Yeah, now you're jumping. I want
Yeah.
that first part of the word, but yeah.
Okay.
So the first part is the probability of observing a value as extreme. Good. And if we want, when we're thinking about our null hypothesis and our alternative hypothesis and all those things, it's more missing two words. To equal to, yeah, a value equal to or more extreme compared to what? Compared to what have we been comparing against?
So the cutoff.
So in our z-score, right? When we calculate a z-score, we're taking our samples average and we're comparing it against something. Which be? We're trying to take like when we think about like our null hypothesis, right? Our null hypothesis says what? So in this case, it was I already forgot what we were doing to the kids. Program. So it was the mu of the program. And what were we comparing that against in our null hypothesis? No program. No program. Otherwise known as the population. The average person. So the probability of observing a value equal to or more extreme than the population. And then if you had magical words, that would get you a meets expectations on the p-value comprehension check and a need revisions if you forgot those magical words.
Assuming that the null is true.
Assuming that the null is true. That last piece is critical to our ability to do statistics the way we do that. We start from a place in the world where we assume that there is no difference. We assume that the null is true. And our p-value tells us what is the probability, what is the likelihood you would observe at least this value, if not a more extreme value, if we assume that there is no true difference. Without the assuming that the null is true, everything that we've been working towards like doesn't appear. The math doesn't work. So we have to say assuming the null is true. It's not a percent, it's a proportion. P-values are proportions. So they too range between what two numbers as a proportion? 0 and 1. If you report a p-value with a percent symbol on it, stop, erase, take a step back, walk away from the percentage. Okay, give me a proportion. Because it is a probability, it's a proportion. We were talking about measures of central tendency and how we usually use a mean, right? No. See, this is the problem with me. Misplace everything. Oh, there it is. Okay, good. We can have a distribution that looks like this. We've talked about distributions that look like this and distributions that look like this. Top one, what's it called? Or it's like characteristics, how you describe it? Normal and symmetric, unimodal as well, right? Like there's one mode. And if it's unimodal symmetric, where are our measures of central tendency? All of them? Yes. They all are here. The mean, the median, the mode, they're all the same. Pick that. If you write that the distribution is unimodal symmetric, they should all be the same. They should point to the same place. Here, the second one, what do we call that? Yeah. Positively skewed. Pause. Or right skew. Great. And where is our mode for our positive and right skew?
Before the.
Okay, this would be, nope. That's the peak, right? Here's our mode. Now the big one here is the mean and median. You obviously don't know the values, so you can't tell me exactly where the mean and median are. But you can tell me where they are in relation to each other. So which one, the mean or the median, is closer to the mode? Right in that way. which one is closer to the mode? The median. Why is the median closer to the mode?
Take the middle value.
The mean's going to be pulled, right? Think about this, like these are all, imagine this is all like 1 through 10, right? This is 1, this is 10, and then out here is a million, right? 1 million. There's just one observation of a million. The 50 percentile is going to land somewhere over here, 50% of our values. But the means would get pulled up because of a million. And so you know that if it's positive skewed, mode, median, mean. If it's negative skewed, reading left to right, which ones do we encounter?
Can you repeat the question? Sorry.
Yeah. No, I'll just say it different. I've said it weird. Where's the mode for our bottom one? At the peak again, right? What do we call this distribution?
Negative left skewed.
Negative or left. And which one is closer to the mode? In this case, the mean or the median?
Median.
The median again. Again, we don't necessarily know where, but we know median is over here, and we know mean is still left. The mean moves towards the tail. Question, who has red? 1, 2, 3, 4, 5, 6, 7. Anyone else have red on the side? Hold it up high. Let me try. Gotcha. Red. 7, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Ooh, that hurts. 15, 16, 17, 18. All right. Sorry about that. Really, had hope. I gave you all class Wednesday to watch Wednesday and Friday's video. So today's recording said there's this really annoying formula for calculating pooled degrees of freedom for t-test. And if more than half of you wore red, then we wouldn't have to use it on the comprehension check. And I said wore red, and I was very generous. I was like, bring in anything that's red. You don't have to wear red. You can have a red piece of paper, red pen, anything, and you wouldn't have to do it on the comprehension check. But it is critical that you watch before class. Okay. I know you're all like, comprehension check 2 didn't go great. And I'm willing to spend time in class walking through stuff. But a lot of the stuff is also things that we have, like, we're way past this stuff at this point, right? And so email me with questions, right? People should be coming to my office hours a lot more than they are, and the office hours are all the time. Really, just I'm here this semester every day of the week for far too long. And watch the videos, take notes on the videos. Don't just skip through it trying to get to the quizzes. That's not the point of the flipped classroom approach. It is literally you sit there and you work through the problems. If you're not working through the problems and you're coming to class confused, like that's not on me. The design of this class is that you're doing the outside work, right? So, I mean, I guess the answer could just be that no one does the independent samples t-test comprehension check. That would avoid the problem. But if you choose to do it, it's going to be longer because it's going to now require the calculating the pool degrees of freedom, which I will include on the formula sheet. It's just annoying to calculate. So I hope you have a good break. Please enjoy it. Get some rest. We are now It feels like much more than halfway through the semester. And I do want to help you succeed, but you got to meet me halfway. And that also is giving yourself some of that ownership too. All right. So have a good one, and I'll see you when we come back.